Hello students, welcome to Eshwari Thaniksha channel. Students, today we are going to start organic chemistry series. So if you are finding organic chemistry difficult, go through this. 100% sure you are going to get full marks in organic chemistry. Your confidence level will be boosted. So what you are going to study in this video is, students, you know that NCERT should be studied line by line. Only you can score very good marks in NEET examination. So see here, instead of learning each and every line, since it is time consuming, all the important concepts I have written in the stick notes here. So you can see I have written stick notes, the important points I have written here. So instead of going through each and every line, so go through this stick notes. It will save your time. So minimum 6 times you have to revise each chapter. So how much time it will take, how much time it will consume. So if you are using this method, 5 to 10 minutes is enough to revise one chapter. And also you can see here I have attached previous year questions, how the question can be asked, and here you can make comparison and you can study. So here you can see I have attached all the stick notes. And also what we are going to learn is, see here, tricks I have attached. So use these tricks so that you can remember everything very well. And also we are going to learn examples. So each and every example we are going to learn in this video. And also in text question, if it is there, we are going to solve in text question as well. So it will be 100% useful to you. So let us start this chapter, that is haloalkanes and haloarenes. So first page, what is very important is only learn this much. What are haloalkanes? So if halogen, X is called as halogen. If halogen is attached to sp3 carbon of alkyl group, then it is called as haloalkane. If halogen is attached to sp2 carbon of aryl group, that is benzene, it is called as haloarenes. And then chloramphenicol, it is an antibiotic used for treatment of typhoid fever. And then thyroxine, that is iodine containing hormone, it is used for treatment of goiter. And then chloroquine, it is used in the treatment of malaria. And then halothane, it is used as anesthetic. So learn only this much from the first page. We will go for the second page. So in second page, what is more important? So what is more important in the second page is, you should know what is allylic halide. Allylic halide meaning is, halogen will be attached to sp3 carbon, and that sp3 carbon will be attached to carbon-carbon double bond. Benzylic meaning is, halogen should be attached to sp3 carbon, and then sp3 carbon will be attached to benzene ring. So here you can see NEET 2023, this question is asked. So before going through, we will see what is vinyl and aryl as well. So here you see vinylic halide. So halogen is attached to sp2 carbon, that is double bonded carbon atom. And here in aryl halide, halogen will be attached to sp2 carbon of the benzene ring. So here you can make comparisons here. So if it is sp2 carbon, these two options you have to select. If halogen is attached to sp3 carbon, then from this you have to choose one. So let us solve NEET 2023 question. The given compound, so this is the compound which is given, is an example of 4 options are given: vinyl, benzyl, aryl, allylic. So we will see halogen is attached to which type of carbon atom. So halogen is attached to sp3 carbon. So how you know that this is sp3 carbon? If single bond is present everywhere, see here, this carbon has single bond, single bond, single bond and single bond. So if single bond is present, then this is sp3 carbon. So if it is sp3 carbon, what is the two option for us? sp3 carbon means it will be allylic or benzylic. So we will see. And this carbon is attached to carbon-carbon double bond, which is outside the benzene ring. Therefore, it is allylic halide. So this is how you have to answer. So this much you should know from this page. So here it is given about vinylic and arylic halide. And here next they have given about two types of halide, which is geminal halide and vicinal halide. So what is that? See, geminal dihalide meaning is same type of halogen should be connected to one carbon. So this is called as geminal dihalide. Vicinal dihalide is same type of halogen should be connected to different carbon atoms. So see here what is given. The dihalo compounds having both halogen atom are further classified as geminal dihalide when both the halogen atoms are present on the same carbon atom. Then it is geminal dihalide. So vicinal dihalide is when halogen atoms are present on adjacent carbon atom. So adjacent carbon atom meaning is next to next carbon atom it should be present. Then it is called as vicinal dihalide. So this much you have to learn from this page. Next is IUPAC nomenclature. So students, tricks on IUPAC nomenclature I have already made. Go through those videos, 100% it will be useful to you. Next we will go for nature of CX bond, that is carbon halogen bond. So here halogen, you know that they are highly electronegative when compared to that of carbon. Therefore, they will pull this bonded electron towards themselves. As a result, they are going to get partial negative sign and carbon atom is going to get partial positive sign. So this much you learn from here. Next, you should learn this table, that is about bond length, bond enthalpy, dipole moment. For this, I have written the trick here. So what is the trick you have to learn is change in electronegativity. If it is increasing, dipole moment also increases. So let us see how. See in the table, this is carbon fluorine bond. So carbon and then fluorine bond. So here electronegativity of carbon is 2.0 and then fluorine atom is 4.0 electronegativity. What is the difference here? The difference is 2. We will take last one and compare. So carbon is 2.0 and iodine is 2.6. So what is the difference? Difference is 0.6. Where the difference is more, the difference will be more here. Electronegativity difference is high here. So if the electronegativity difference is high, then the dipole moment also should be high. So therefore dipole moment should increase in this order. For iodine it is less, for fluorine it is more. So dipole moment should increase in this order. Check the value: 1.84, 1.86, 1.83, 1.63. So here chlorine is more when compared to fluorine. So that is the exception. See here, chlorine is more. The dipole moment I have written here. For chlorine it is more, fluorine second, bromine and iodine. So since there is exception, I have highlighted here so that it is easily visible to you. So what is the exception here? Why this exception is? Carbon chlorine, the bond, if you see, the bond length is more. Since the bond length is more, dipole moment also will be more. So see here bond length value. For CF, the bond length is 139. Whereas CCl, the bond length is 178. So here what is the difference? Difference is almost 40. Whereas here if you see the difference, it will be 10 to 20. Since here the difference is very high, so the bond length here it is more. If the bond length is more, because of that you can see this exception. So learn this order. Dipole moment order will be this. Next is bond length and bond length and bond enthalpy. Bond enthalpy is nothing but bond energy. So what is the trick we are going to use is bond length is inversely proportional to bond energy. So bond length, you see, for iodine it is more, and then bromine, and then chlorine, and then fluorine. For bond enthalpy it will be reverse order. Fluorine it is more, chlorine, bromine and iodine both are inversely proportional to each other. Here there is no exception. Only for dipole moment there is exception. Chlorine is more than fluorine, but here there is no exception. You can learn this order. Next we will go for methods of preparation of haloalkanes. So here this is very important, students. From here every year at least one question is asked. So how we are going to learn this is, the first two reactions. So first two reactions I have written here in detail. We will see this. So first we will see the first reaction, that is first reaction is called as Lucas reagent. Whenever you see HCl in the presence of zinc chloride, so see the reaction HCl in the presence of zinc chloride, what is happening is OH group is substituted with Cl. So here Cl is there, therefore OH will be replaced with the Cl. So this is called as Lucas reagent. Zinc chloride in the presence of HCl, it is called as Lucas reagent. So this one same thing you will learn in alcohol chapter as well. So once you read here, so there you can just revise it. So this Lucas reagent is used to distinguish between primary, secondary and tertiary alcohol. So if it is tertiary alcohol, turbidity will appear immediately or instantaneously. Meaning is, as soon as you add this Lucas reagent, white color precipitate will appear, which is called as turbidity. Whereas for secondary alcohol, it will take 5 to 10 minutes to appear that turbidity. If it is primary alcohol, in the textbook it is given there is no turbidity, but after 30 minutes the turbidity will appear. So remember, in the question paper if it is given, turbidity will appear after 30 minutes. If it is given, it is primary alcohol. Or suppose if it is given, no turbidity appears, even then it is primary alcohol. So learn this timing. So immediately 5 to 10 minutes, and here it is 30 minutes. So this is Lucas reagent. Second is alcohol when you are treating with sodium bromide in the presence of sulfuric acid. Again OH group will be replaced with Br, because here we are taking Br. And if you are taking NaI, sodium iodide, or if you are taking potassium iodide, OH should be replaced with iodine. You will get Ri. So here we are using sulfuric acid for NaBr. If you are using iodine, we have to use phosphoric acid. So phosphoric acid is H3PO4. Remember this formula. Phosphoric acid is H3PO4. So here the question can be asked, why sulfuric acid is not used here? Instead of that we are using phosphoric acid. Why sulfuric acid is not used? Because see here the reason also I have written. Sulfuric acid is not used because it is strong oxidizing agent. What it will do is, it will convert hydrogen iodide which is formed in the reaction to iodine. So that is why we are not using sulfuric acid when iodine is taken. So for second here we are not taking sulfuric acid, and for the first one we are taking sulfuric acid. So see a second reaction, alcohol when it is treated with sodium bromide in the presence of sulfuric acid, we are getting RBr. And remember one more point here, very important. First and second reaction, it proceeds through SN1 reaction. So SN1 mechanism I have given in detail, so you can go through it if you want. So SN1 mechanism meaning is, it produces carbocation. So it forms carbocation. So students, remember, wherever carbocation is formed, there you have to check for rearrangement, because stable carbocation is preferred. So that is why for the first and second reaction, whenever carbocation is formed, check for the possibility of rearrangement. So if rearrangement is possible, do rearrangement and then you attach the halogen to that carbon atom, because they proceed through SN1 mechanism. And then this reactions, see I have marked as 3. 1, 2, 3. So all this, that is phosphorus related reagents. So these are undergoing through SN2 mechanism. So if it is SN2 mechanism, then there is no carbocation formation. So here rearrangement is not possible. Only for the first two you have to check for rearrangement. So here if you are taking PX3, so here you can see phosphorus trihalide. So X3, it can be chlorine or it can be bromine. So and next is PCl5. So PCl5, if you are taking with PCl5 or PX3 or red phosphorus, what happens is OH group everywhere should be replaced by halogen. So here what halogen you are taking? So you have to replace this OH group with the halogen. So remove this OH, place Cl there. Remove this OH, and here the halogen what you have taken, you have to place it over there. But what is very important, all these are major product, but what here it is important is these two byproduct. So this is what is asked in NEET examination. So what is the byproduct formed when you are using PX3? So the byproduct formed here, it is, make a note of it, H3PO3 is phosphorus acid. Phosphoric acid is H3PO4. H3PO3 is phosphorus acid will be formed. In case of PCl5, you can see POCl3 will be formed, which is phosphorus oxychloride. So this is what you have to learn, very important, which is asked in NEET examination. And then next is fourth with thionyl chloride. SOCl2 is called as thionyl chloride. Alcohol when you are treating with thionyl chloride. So again remove OH and we are placing halogen over there, which is Cl. And the byproducts are SO2 and HCl. So this is one good method. So if they ask which is the good method to form haloalkane, so this will be one good method. Why? Because these two are gases which is formed, which can be liberated, and we are going to get haloalkane. SO2 is a gas and HCl is also a gas which will go out. So you will get this as the product. So here we will see what is given. The hydroxyl group of alcohol is replaced by halogen on reaction with concentrated halogen acid. So students, halogen acid meaning is, halogen is Cl. Halogen acid meaning is HCl, HBr, HI, all these are called as halogen acid. Then phosphorus halide, thionyl chloride. Thionyl chloride is preferred. I told you thionyl chloride is preferred because SO2 and HCl is a gas, so which will be going out easily. So the product we can get. The two gaseous products are escapable. Hence the reaction gives pure alkyl halide. The reaction of primary and secondary alcohol with HCl requires the presence of catalyst zinc chloride, while tertiary alcohol, the reaction is conducted by simply shaking the alcohol with concentrated HCl at room temperature. So here for primary and secondary alcohol you need zinc chloride. For tertiary alcohol you just shake, immediately, instantaneously you will be getting that turbidity. And one more important point here is the rate of the reaction. So first and second reaction I said it proceeds through carbocation. So carbocation stability, you know that tertiary greater than secondary greater than primary carbocation. So the rate of the reaction will be in this order. So you can see all this reaction with the important points I have written here. So here thionyl chloride is good method. So for the preparation of haloalkane, thionyl chloride is a good method because these two are gases which is easily escapable and you will be getting this product. So just go through it. All the important points I have covered. And next, the above method is not applicable for preparation of aryl halide. Aryl halide meaning is halogen if it is attached to benzene ring. So here we cannot prepare this because the carbon oxygen bond in the phenol has partial double bond character. So meaning is, so this is phenol, benzene ring, and here this is phenol. So this is having double bond character. So that is why. So you can see here carbon oxygen bond in phenol has partial double bond character. So this is oxygen and this is carbon. So this bond has partial double bond character. So breaking this bond will be very difficult. Therefore this is not applicable for the preparation of aryl halide. So this you have to make a note. So I have highlighted this, you can see, and also I have written here, you can just check it out. Because of partial double bond character, so it is not easy to break this bond. So next is preparation from hydrocarbons, from alkanes by free radical halogenation. That is, alkane you take and then in the presence of chlorine and in the presence of UV light. So what happens is it is a free radical reaction. You can see hydrogen will be replaced with chlorine. So you can get mono haloalkanes or polyhaloalkanes. Meaning is, mono meaning is only one halogen is attached. Polyhalkane meaning is more than one halogen can be attached to the alkyl group. So see here, alkane is there, and then we are taking chlorine in the presence of UV light. So here, how many products are formed? There are two products which is formed. So how do you know that two products are formed? It depends on the type of hydrogen atom which is present here. Here, how many types of hydrogen atoms are present? So see here, how many carbon atoms are there? 1, 2, 3, 4. So this is a symmetry molecule. Meaning is this you can break into exactly two half. So when you are breaking this into exactly two half, one side you count. So here 1, 2. So two types of hydrogens are there. Therefore two types of compound you will get. So what you should do is once you remove one hydrogen and place chlorine over here. So the first product you will get. So CH3, if you remove hydrogen, it becomes CH2. And then in that place you are placing Cl. Second product is remove one hydrogen from here and place Cl. So see here, it becomes CH and then one chlorine you are attaching. So two products you are getting. And then from alkene. So from alkene is addition of hydrogen halide. So what happens is carbon-carbon double bond if it is present, and if you are taking alkyl halide. So always remember that it follows Markovnikov's rule. So what is this Markovnikov's rule is, whenever two products are formed, one will be a major product and another will be a minor product. So how we are going to find the major product is, always break one bond. So double bond is present, break the double bond, place hydrogen to the carbon containing more number of hydrogen atom, and halogen you should attach to the carbon containing less number of hydrogen atom. So example I'll show you. So see here, this is carbon-carbon double bond. So check this carbon atom, where more number of hydrogen atom is present. Hydrogen atom is present here, two hydrogen atoms, and to this carbon only one hydrogen atom is present. So here hydrogen atoms are more. Therefore hydrogen should be added to the carbon containing more number of hydrogen. So break this double bond, add hydrogen here and then iodine here. So see here, major product. We have added hydrogen to this carbon, and to the center carbon we have added iodine. So that will be the major product. So this is according to Markovnikov's rule. So I have written here. So add hydrogen to the carbon-carbon double bond having more number of hydrogen atom. And next is bromine in the presence of CCl4. So this is the test for unsaturation. That is, if you take alkene, add bromine in CCl4. So bromine in CCl4, it will be reddish brown in color. So as soon as you add this into double bonded compound, what will happen is that brown color will get discharged. So it will become colorless. So what happens is double bond will break and you have to add one bromine here and one bromine to this carbon atom. So you can see here, to one carbon one bromine, and to another carbon you have to add one bromine. So that is addition of halogen. So see here, it becomes vicinal dibromide. So next we will go for the example. Example 6.3. Identify all the possible monochlorostructural isomers expected to be formed on free radical monochlorination. So a compound is given and you have to form, what we want is monochlorostructural isomers are required. So I told you that see the number or see the type of hydrogen atom. So see the same structure. How many carbon atoms are there? 1, CH3 2 times. So 2 carbon atom here. Third, 4, 5. Totally there are 5 carbon atoms here. So same structure I have written here. CH3 2 times. So CH3 2 times, it is attached to this carbon, and then CH2 CH3, CH2 CH3. So this is the formula which is given here. So here check how many types of hydrogen atoms are there. So here, how to find out is, this hydrogen is attached to this carbon. So this carbon is primary carbon, and here this carbon is secondary carbon, and this is tertiary carbon. This is primary carbon, this is primary carbon. So now primary carbon, primary carbon, primary carbon. So we have 3 primary carbon. So whether it is one and the same or different, we have to check. So see here, this primary carbon is attached to secondary carbon, Whereas here this primary carbon is attached to tertiary carbon, and this primary carbon is also attached to tertiary carbon. So these two are same. This is different because this is attached to secondary carbon. So therefore the type of hydrogen atom present here is, this is one type of hydrogen present, this is second type of hydrogen, this is third, this is fourth, this is fourth, because these two are same. So therefore four types of hydrogen atoms are present. If four types of hydrogen atoms are there, see here in the given molecule there are four different types of hydrogen atoms are present. Therefore replace it, you will be getting four product. So first what I'll do is replace here hydrogen with chlorine. So here the product, they are starting from here. So first replace one hydrogen with the chlorine, so it becomes CH2Cl. And second product is replace one hydrogen with chlorine, CHCl. Next is replace this hydrogen with chlorine, so you can see here it becomes CCl. Next is from here or here, anywhere it is the same. So replace one hydrogen with chlorine, so you can see here one hydrogen is replaced with chlorine. So totally you will be getting four product. So this is the structure which is given here. So next is halogen exchange method. So halogen exchange method, here you can see there are two reactions which is very important, name reaction. So that is Finkelstein reaction and Schwarz reaction. So students, if you need to learn the mechanism, I have done a separate video for that. So if you want to know, you can go through that mechanism as well. So here simply what you have to remember is Finkelstein reaction is used for the preparation of iodine, halogen iodine, haloiodine, alkyl iodine. That is, remember like this, Fin, Fin, I is present. Remember I means iodine. So in the preparation of alkyl iodine, we are going to use this Finkelstein reaction. So what you should do is take Rx. So here X can be chlorine or it can be bromine. You are treating with sodium iodide in the presence of acetone, you will be getting. So this will be replaced with iodine. And here one important question which can be asked is why we are using this dry iodine. So here the reason also I have given. So why we are using dry acetone is it will precipitate NaCl or NaBr which is formed. See the reaction here. In the reaction, this halogen is replaced by the iodine, and suppose if it is Cl here, Na will combine with Cl and here NaCl will be formed. Suppose if this is Br, Na will combine with Br and here it will be NaBr. So the NaBr or NaCl which is formed here will be precipitated by dry acetone. Precipitated meaning is it will be in the solid form which you can remove, separate out. So remove this, you will be having only this product now. So to precipitate NaCl and Br, we are using dry acetone. Second is it helps in forward reaction which is according to Le-Chatelier's principle. So Le-Chatelier's principle, I have done tricks on that. So if you don't know Le-Chatelier's principle, you can go through that video, go to the playlist and go through it. So what is Le-Chatelier's principle is whenever you decrease the concentration on one side. So here this is the reactant side and this is the product side. So product side we are removing this. So meaning is product side we are decreasing the concentration. So the reaction will proceed in the direction where the concentration will decrease. Since the concentration is decreasing on the product side, the reaction will proceed in the forward direction according to Le-Chatelier's principle. So this much you have to know. So I have already written all the points here. Go through this. Next is Schwarz reaction. So in Schwarz reaction we are going to prepare alkyl fluorine. So that is take CH3Br, treat with metallic fluoride. So here metallic fluoride. So metal what we are using is silver. You can use mercury, you can use cobalt and Sb. Sb is nothing but antimony. So you can use silver, mercury, cobalt, antimony. So this also it can be asked in NEET examination. So which are the other metallic fluoride which is used in Schwarz reaction? So remember these four metals. So these are the metal fluorides we are using in the preparation of this fluorine compound. So students, next video I'll start from here, that is preparation of haloarenes. So students, go through this, all the important concepts I have covered here itself. So just go through this. I think it will take only few minutes to go through this. Several times you can revise for your examination. Students, if you find this video useful, you can subscribe the channel and also share this video with maximum number of students. It will be helpful to others as well. So all the very best students, prepare well for your examination. I'll meet you in the next video. Now we are going to study preparation of haloarenes. Haloarenes meaning is halogen will be directly attached to benzene ring. So how to prepare is, take toluene. Toluene is methyl group attached to benzene ring is called as toluene. Toluene, when you are treating with chlorine or bromine in the presence of Fe, that is in the presence of iron chloride, so which is a Lewis acid, in dark condition, you will get two products. That is, this halogen will be substituted at the ortho position and para positions. So you know that this will be the ortho position. So one product you will get at the ortho position, and this is the para position, and halogen will be substituted at the para position. So this ortho and para product can be separated easily because they have huge difference in their melting point. So melting point of para product will be high when compared to that of the ortho product. So what is the reason for that is, the reason is it is a symmetry molecule. Since it is symmetric molecule, it fits well in the crystal lattice. So that is why para product will be having high melting point. So here if you are using iodine, so if you are using iodine, you have to use oxidizing agent like nitric acid or HiO4. So because the iodine which is used here, in the product you will be getting Hi. So when you are using the oxidizing agent, the oxidizing agent will convert Hi back to iodine. So it will become a reversible process. So here you can see, reaction with iodine are reversible in nature and requires the presence of oxidizing agent like nitric acid or HiO4 to oxidize Hi formed during the iodination. Fluoro compounds are not prepared by this method due to high reactivity of fluorine. So we are not using fluorine because it is highly reactive in nature. So we are going to use chlorine, or you can use bromine in the presence of Fe. So you will be getting these two products. When you are using iodine, you have to use strong oxidizing agent like nitric acid or HiO4. Next is Sand-Meyer's reaction. So this is very important. So many times this question is asked in the NEET examination. So here you have to take aromatic primary amine. So here aromatic primary amine is aniline. So this is aniline. Aniline is NH2 group. If it is directly attached to benzene ring, it is called as aniline. So aniline you are treating with sodium nitrite plus Hi. The temperature should be very low. So at cold condition, that is 273 to 278 Kelvin. So if you convert to degree Celsius, it will be 0 degree to 5 degree Celsius. So temperature is very low, you have to maintain. So you will be getting benzene diazonium salt will be formed. So this is the salt which is formed. So when you are treating this with cuprous chloride, what will happen is this chlorine will be substituted here. So you have to remove this and then place chlorine. So you will get chlorine directly attached to benzene ring. So in place of CuCl2, that is cuprous chloride, if you are using cuprous bromide, Cu2Br2. So what is the product obtained? So in this place bromine will be attached. So here you will be getting Br. So depending on the reagent, you will get chlorobenzene or bromobenzene. If it is cuprous chloride, chlorobenzene. If it is cuprous bromide, Cu2Br2, then it will be bromobenzene will be formed. So if you want iodine to be attached, so you have to treat benzene diazonium salt with potassium iodide. Then this iodine will get attached here. So you will be getting iodobenzene as the product. So this is Sand-Meyer's reaction. So you can see here which is given. You can go through it once. So everything in the condensed form I have given here. So revise this several times. So next we will see example. Write the product of the following reactions. So first one. So here you can see a compound is given. It is treated with HBr. So whenever HBr is there and there is a double bond, so you have to use Markovnikov's rule. So what you have to do is you have to break this double bond. So when you are breaking this double bond, hydrogen should be added to one carbon atom and bromine should be added to another carbon atom of the double bond. So where you will add is according to Markovnikov's rule. Hydrogen should be added to the carbon atom containing more number of hydrogen atom. This carbon, how many hydrogen atom it has? It has only one hydrogen atom. This carbon, how many hydrogen atom it has? It has two hydrogen atoms. So more hydrogen atom it has. Therefore hydrogen should be added to this carbon and bromine should be added to this carbon. So here you can see this is the product obtained. Second, so again you can see there is a double bond and HCl is there. So use Markovnikov's rule. So break the double bond, add hydrogen to the carbon containing more number of hydrogen atom. So here you will add to this carbon and chlorine you will add to this carbon. So you can see this is the product obtained. And here again you can see there is a double bond and there is HBr. So whenever peroxide is there, so it will be anti-Markovnikov's rule. So if peroxide is absent, then it will be Markovnikov's rule. If peroxide is present, then it will be anti-Markovnikov's rule you have to use. So here anti-Markovnikov's rule is hydrogen should be added to the carbon containing less number of hydrogen atom. So this carbon is having less number of hydrogen. So add hydrogen to this carbon and add bromine to this carbon. So you can see this is the product which is obtained. So next in text questions we will see why sulfuric acid is not used during the reaction of alcohols with hydrogen iodide. So already this I discussed in the first video. So why we are not using sulfuric acid is sulfuric acid is a strong oxidizing agent. It will convert Hi which is formed in the reaction to iodine. So that is why we are not using sulfuric acid. Second, next question, write structures of different dihalogen derivatives of propane. So propane means how many carbon atoms will be present? There will be 3 carbon atoms present. Dihalogen meaning is 2 halogen you have to add to propane. So see here, these are the 4 possible product. So 3 carbon atom, propane means 3 carbon atom. So dihalogen means one halogen attached here and second halogen attached to this carbon. Another probability is attached to this carbon and then halogen to this carbon. Third probability is to the same carbon, terminal carbon we can attach 2 halogens. And next probability is to the center carbon we can attach 2 halogens. So these are the 4 possible products obtained in the for propane. Next, among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination yields. So here a single monochloride. So single monochloride means the compound should be having only one type of hydrogen. So see here, this is the answer. How many types of hydrogens are present here? See this. Here hydrogens are attached to this carbon. So this carbon is primary carbon. Even here hydrogens are attached to this carbon and this carbon is primary. Even this is primary carbon, this is primary carbon. So all the primary carbons are attached to this carbon. So all the hydrogen atoms here are equivalent in nature. Therefore it will give monochloride, single monochloride. So the answer for first one will be this. 3 isomeric monochloride, meaning is 3 means 3 different types of hydrogen should be present. So this is the answer. So let us see whether 3 types of hydrogen atoms are present in this. So see here, this is a symmetric molecule. That is exactly you can break this into 2 half. So here this is one type of hydrogen, second type of hydrogen and third type of hydrogen. So 3 different types of hydrogens are there. So this will form 3 isomeric monochloride. So this is the second answer. 4 isomeric monochloride, means 4 different hydrogen atoms should be present. So see in this compound whether 4 different hydrogen atoms are present. So this is primary carbon, this is secondary carbon, this is tertiary carbon, this is primary carbon, this is primary carbon. So here you can see 3 primary carbons are present. Out of these 3 primary carbons, these 2 are same because these 2 are attached to tertiary carbon atom. So these 2 will be one type of hydrogen atom. This is second type, this is third type, this is fourth type. So 4 different types of hydrogen atoms are there. Therefore this will give 4 different isomeric monochlorides. So answer for this will be this. Next 6.5, draw the structures of major monohalo product in each of the following. So you can see here thionyl chloride is there. So in the preparation of alcohol in the first video we studied this reaction of thionyl chloride, which is a good reagent for the preparation of alcohol. So if OH group is there, remove OH group and place Cl over there. So what is the product you will get? You will get product like this. So in place of OH, Cl you have to place. Second, so reactant is given bromine in the presence of UV light. So whenever bromine is there in the presence of UV light, it is free radical mechanism. So if it is free radical mechanism, don't touch the double bond. So here side chain, see which will form stable free radical. You know that tertiary free radical is stable than secondary, which is stable than primary free radical. So here if I form free radical, this is primary. If I form free radical, this is secondary. So secondary will be more stable. Therefore remove one hydrogen from here and place bromine from here. So here the product can be written like this. So here CH, Br, CH3 and then NO2. So this is the product. Next here HCl is present and you can see 2 alcohols are present. So which alcohol you have to substitute with chlorine? So here always remember, if alcohol group is directly attached to benzene ring, so this is very difficult to break this bond because this will be having the partial double bond character. So that is why breaking this bond will be difficult. So only you have to replace this with Cl. So remove this OH and place a Cl over here. So this will be the product. So next is there is a compound and here HI is given. So whenever you see a double bond and HI, so what you have to think of is, you have to think of Markovnikov's rule. So break this double bond, add hydrogen to the carbon containing more number of hydrogen atom. So here this carbon has 1 hydrogen atom and this carbon doesn't have hydrogen atom. Therefore add hydrogen to this carbon and add iodine to this carbon. So what is the product obtained? So you will be getting product like this. So here CH3, I and then here H. So already 1 hydrogen is existing here. So this is the product which is obtained. So next, so reactant you are treating with sodium iodide. So this is halogen exchange method. So in the first video we have already studied halogen exchange method. So bromine you are exchanging with iodine. So you will be getting here CH3, CH2, I. This is the product. So next again here you can see there is a double bond and here there is bromine in the presence of UV light. So again this is a free radical mechanism. So students, whenever it is a free radical mechanism, don't touch the double bond. So because bromine in the presence of UV light, it undergoes free radical mechanism. So here this carbon atom will be having 1 hydrogen. So here removing that hydrogen form 1 free radical over here, or even this carbon can form free radical over here. It is one and the same. So here the product will be, so double bond you keep as it is and here you have to attach bromine because free radical should be formed here. The free radical which is formed here is more stable. So therefore attach bromine to this carbon. So this will be the product. Next is physical properties. So what is very important under physical property is you should know about melting point, boiling point and density. So how you will learn about this melting point, boiling point and density is boiling point. If you consider for hydrocarbon, the boiling point will be less compared to that of haloalkane. That is, one hydrogen you will be replacing with halogen. This is haloalkane. See here, because the mass of hydrocarbon will be less when compared to the mass of the haloalkane. So if the mass is high, boiling point is high. So remember this trick. Boiling point is directly proportional to the mass. If mass increases, boiling point also increases. So the mass of haloalkane will be high, therefore boiling point also will be high, and here the boiling point of hydrocarbons will be less. So here I have made a note of it, you can see here. And again, if you are comparing iodine, that is haloalkane where iodine is present, then bromine, chlorine and fluorine. So here for iodine it will be greater, boiling point will be greater compared to bromine, then chlorine and then fluorine. So what is the reason for this is again because of mass. You know that iodine has greater mass when compared to bromine, chlorine and fluorine. So because of higher mass, so this will be having higher boiling point. One more reason is because of charge difference, there is greater force of attraction. So you can see here the reason is given. Increase in size and mass of halogen atom, the magnitude of van der Waals forces also will increase because of difference in their sizes. So van der Waals force of attraction also will be more, because of which the boiling point will be in this order. So you can learn from here. And then if it is branching compounds are given, see here if 3 compounds are given, you have to compare which is having more boiling point and which is having lesser boiling point. Use this trick. That is, boiling point is inversely proportional to branching. Meaning is greater the branching, boiling point will be less. See here there is no branch. Here second compound, 1 branch is present. In the third compound you can see 2 branches are present. So more number of branches are present here. So greater the number of branches, boiling point should be less. So see the boiling point 346 and here you see 375 and here 364. So therefore no branching, boiling point is high. Branching is present, therefore boiling point is less. So use this trick. So boiling point of isomeric dihalobenzenes are very nearly the same. However, para isomers are high melting as compared to their ortho and meta isomers. So this already I told you that para will be having more melting point. We are talking about melting point. So para will be having higher melting point when compared to ortho and meta. This is because of symmetry. That is, para will be symmetry molecule and also it will fit exactly in the crystal lattice. That is why. So here you can see the order of boiling point and melting point. Boiling point, ortho will be greater and then para and then meta. Melting point, if you are comparing, para will be greater and then ortho and then meta. So now comparing the density. So density is directly proportional to mass of the compound. So more the mass, density will be higher. So this is very simple to remember. Remember, density will be directly proportional to the mass. So if mass increases, the density also will increase. And then coming to solubility. So this is very important here. So if you take haloalkane, so here I have written, so take one haloalkane and this is second haloalkane. So between 2 haloalkanes there will be force of attraction. Why there will be force of attraction? This halogen is having partial negative sign and this is having partial positive sign. Again here this carbon is having partial positive sign and halogen is having partial negative sign. Because of this charges, negative and positive charge, you can see there is force of attraction between them. So if you want to break this force of attraction, you have to supply energy. Now we will take water. So in water you know that there will be hydrogen bonding between 2 water molecules. Again to break this hydrogen bonding you have to supply energy. Here you can see there are two different types of bond. Here due to attraction there is a bond formed, and here hydrogen bond is formed. So here two different types of bonds are there, and you are breaking by supplying the energy. So now you take one molecule of haloalkane and then one molecule of water. So here again you can see a bond will be formed. When a bond is formed, energy will be released. The energy released will be very less in amount when compared to the energy what is supplied. Therefore, this will be highly unstable. Therefore, solubility of haloalkane in water is very less. Why? Because of two different kinds of bonds are present, and here the bond formed is also different. Therefore, solubility will be very less in water. So here you can see solubility of haloalkane in water is less, but solubility of haloalkane in organic solvent will be more because of new intermolecular attractions between haloalkanes, and solvent molecules have much the same strength as the one being broken in the separate haloalkanes and solvent molecule. Meaning is, instead of water, if you are taking organic solvent, here the attraction between the haloalkanes and attraction between the organic molecule and the bond formed, almost everything will be similar. Therefore, they are more likely to be soluble in organic solvent compared to water. So in water less soluble, in organic solvent they are more soluble. Arrange each set of, let us see the in-text question now. Arrange each set of compound in order of increasing boiling point. So you know that boiling point is directly proportional to mass. So if mass is more, then boiling point also will be more. So let us see here. So the first one is bromomethane. Bromomethane is CH3Br, bromomethane. Second is bromoform. Bromoform is CHBr3, is called as bromoform. Chloroform, you know that CHCl3. So same way bromoform is CHBr3. Next is chloromethane. Chloromethane is CH3Cl. And then dibromomethane. Dibromomethane is CH2Br2. So dibromomethane. So which is having more boiling point here? So let us compare. So which is having more mass here? So here chlorine is present. Let me take another color. So here you can see chlorine is present. Chlorine is present, and in all this bromine will be present. So chlorine has mass less when compared to that of bromine. So therefore this will be position number 4. So less boiling point. So let us compare these three now. This one, and this one. So here bromine atoms are more. So boiling point will be more because mass is more here. So this is number 1. And this 2 bromine atoms, number 2. And here 1 bromine atom, number 3. Chlorine will be having less mass, number 4. So this is the order of boiling point. Next is 1 chloropropane, isopropyl chloride, and then 1 chlorobutane. So 1 chloropropane meaning is 3 chlorine atoms and 1 halogen, that is chlorine, is attached. Isopropyl chloride is 3 carbon, and you can see 1 branch is present. And then 1 chlorobutane. Butane means 4 carbon atoms are there and 1 chlorine is present. So here 3 carbon, 4 carbon atoms are present. So therefore the mass will be high here. So this is number 1. So boiling point will be high here. And now let us compare these two. So I said you that boiling point is inversely proportional to branching. So that is, here there is a branch and here there is no branch. So since branching is present, boiling point will be less. So this is number 3 and this will be number 2. So I hope you understood. Since 4 carbon atoms are there, mass is very high. So halogens are present in all the 3 compounds, you can see. 1 halogen is present, 1 chlorine, and 1 chlorine. So that is that doesn't make any difference. But here carbon atom 4 are present. here 3 and here 3. So since 4 carbon atoms are there, mass will be high. Therefore, boiling point will be high. This is number 1. If branching is there, boiling point will reduce. Here there is no branching, therefore this is number 2 and this will be number 3 because branching is present. So this is the order. So I hope you understood. So students, remaining we will see in the next video. I hope you like the video. Students, subscribe the channel and also share this video with maximum number of students. All the very best, students. So in this video, we are going to mainly focus on SN1 and SN2 reaction. So here you can see chemical reactions of haloalkanes. So haloalkanes will show 3 types of reactions. First one is nucleophilic substitution reaction, second elimination reaction, and third is reaction with the metals. First we will see nucleophilic substitution reaction. The meaning of nucleophile is they are electron rich species. So usually they are represented as Nu minus. So here you can see haloalkanes are substrates. In this reaction, if you see, Nu minus is called as nucleophile and haloalkanes are called as the substrate, and here X minus is called as the leaving group. Leaving group departs as halide ion. So X will be leaving as X minus. So this is X is called as the leaving group. So why it is called as nucleophilic substitution reaction is nucleophile will be substituted in place of halogen. Therefore, it is called as nucleophilic substitution reaction. And one more important point here is halogen is bonded to sp3 hybridized carbon. So here this carbon is sp3 hybridized. So halogen is bonded to sp3 hybridized carbon. Next, this table is very important. So here what you have to mainly focus is on these reagents KCN, AgCN, KNO2 and AgNO2. That is potassium cyanide, silver cyanide, potassium nitrite, silver nitrite. So all this 4 all called as ambident nucleophile. So ambident nucleophile meaning is they will have 2 nucleophilic center. That is, so cyanide. So in cyanide you can see carbon can also attack alkyl group. Nitrogen can also attack alkyl group. So there are 2 nucleophilic center. Same way in nitrite also, nitrogen can attack alkyl group or oxygen can attack alkyl group. Therefore here 2 nucleophilic centers are present. So here you can see in the table potassium cyanide. Potassium cyanide is ionic in nature. Because of that, it will be breaking as K plus and Cn minus ion. So minus is present on carbon. So now here carbon is also electron rich and nitrogen is also electron rich. But carbon will be attacking R and it will form RCN. So if Cn is attached through carbon, if it is attached to R group, it is called as cyanide. Whereas in silver cyanide is covalent in nature. Therefore, it will not break as Ag plus and Cn minus. So here now nitrogen will be having lone pair of electron. So this nitrogen will attack R group. As a result, RNC will be formed. So nitrogen will be forming bond with R. So then it is called as, if it is NC, then it is called as isonitrile. Same way potassium nitrite. So in potassium nitrite, this is ionic in nature. Therefore, it will be breaking as K plus and NO2 minus. So negative sign will be present on oxygen. So this oxygen will attack R. So you will be getting RON double bond O, which is alkyl nitrite. Whereas silver nitrite, this is covalent in nature. So therefore the bond doesn't break. So now what will happen is nitrogen is going to attack R group. So therefore you will be getting RNO2, which is nothing but nitroalkane. So here you can see cyanides and nitrites possess 2 nucleophilic centers and are called as ambident nucleophile. So cyanide group is a hybrid of 2 contributing structures. That is 2 resonance structures are present. So you can see this is one resonance structure and this is another RS, that is resonance structures. So here carbon has negative sign and nitrogen will be having lone pair of electron. So here carbon will be attacking this carbon of the alkyl group and a bond is formed between carbon and carbon. So why nitrogen doesn't attack? So nitrogen also has a lone pair of electron, but nitrogen will not attack carbon, only this carbon is attacking. So what is the reason? So the reason is given here. Carbon carbon bond is more stable than carbon nitrogen bond. So here the carbon carbon bond which is formed, so this is more stable. Instead, if C and N bond is formed, this is not stable, so this is more stable. So next we can see here mechanism. SN2, that is substitution nucleophilic bimolecular. SN2 meaning is substitution nucleophilic bimolecular reaction. So this is a second order reaction, meaning is the rate is proportional to concentration of two reagents, that is nucleophile and haloalkanes. So you can see this is the reaction. So OH minus is called as nucleophile and this is alkyl halide. So nucleophile will attack the carbon. Simultaneously you can see Cl minus will be leaving. So a transition state will be there. In the transition state you can see the bond is formed by OH and here the bond is breaking simultaneously. And this transition state is unstable. Why it is unstable? Because carbon is bonded to 5 atoms. You can see 1, 2, 3, 4, 5. So this carbon atom is bonded to 5 other atoms. Therefore, it is highly unstable in nature. And this is the product formed. So since here nucleophile is attacking the carbon atom from behind. So here you can see the configuration will be inverted. Inversion of configuration will take place in SN2 reaction. So here you can see this is a single step reaction. So if you see the reaction, all this are taking place in one step. So if it is single step, the same step will be rate determining step. So rate determining step will be the slowest step. Since only one step is there, this itself will be the rate determining step. And here you can see as a result configuration will be inverted. Inversion of configuration will take place. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms. So already I told you that. So this is the transition state where carbon is bonded to 5 other atoms. Therefore, it is highly unstable and this cannot be isolated. Since it is unstable, remember transition state is unstable. Therefore, this cannot be isolated. And then configuration. So what is configuration? Is spatial arrangement of functional groups around carbon is called as configuration. So this is carbon atom. So arrangement of groups around it is called as configuration. So next we will go for the order of reactivity of SN2 reaction. So the order of reactivity is for methyl it is greater, then primary, secondary is greater than tertiary. So why it is, we will see here. So this is methyl group. So you can see C, H, H and H. So you know that nucleophile will be attacking from back side and halogen will be leaving from this side. Since it is attacking from behind, so here if smaller groups are there, so attacking the carbon atom becomes easy. Whereas here you see in the primary carbon, so in the primary carbon a bigger group is there. So because of that, so entering the nucleophile attacking the carbon atom becomes little difficult. Whereas in secondary carbon, if you see, still bigger groups, so 2 bigger groups are there. Therefore, nucleophile attacking the carbon atom becomes difficult. Whereas in tertiary carbon, you can see 3 big groups are there. Therefore, it becomes very, very difficult for the nucleophile. See here, 0% chance for the nucleophile to attack carbon atom because of steric hindrance. Steric hindrance meaning is there are bigger groups, so therefore nucleophile cannot attack the carbon atom. So therefore for the order of reactivity will be, for primary halide it is greater, secondary, and then tertiary. And before that there is methyl group. If it is methyl, so the rate of reaction will be fast, then primary, then secondary, and then tertiary. Next we will go for SN1 reaction, that is substitution nucleophilic unimolecular. One meaning is unimolecular reaction. So it is a first order kinetics because the rate of the reaction depends on concentration of only alkyl halide. So we will see why. So here let us see this example what they have given. So this is tertiary butyl bromide. So here we have a nucleophile. So nucleophile will replace this Br and you can see OH is formed. And this reaction takes place in 2 steps. So here you can see 2 steps. In the first step, what is happening? In the first step, you can see Br leaves us Br minus and a carbocation is formed in the first step. And in the second step, you can see nucleophile is coming and attacking the positive sign of the carbocation and it forms alcohol. So students, here the first step is the slowest step. So always remember that RDS, rate determining step. Rate determining step always will be the slow step. So here this is the rate determining step, and in the rate determining step you can see there is carbocation formation. So stable the carbocation, the rate of the reaction will be faster, and nucleophile is not seen in the slow step. It comes only in the second step. Therefore the rate depends only on the formation of carbocation. So here you can see step 1 is the slowest and it is reversible. It involves CBr, that is the bond between C and Br breaks, for which the energy is obtained through solvation of halide ion with the proton of protic solvent. So here in SN1 reaction we are going to use polar protic solvent. So I have written the difference as well. You can go through this. SN1 it takes place in 2 steps. SN2 it takes place in 1 step. And here it proceeds through carbocation formation. Whenever carbocation is formed, you have to check for rearrangement. SN2, so it goes through transition state which is highly unstable, and here there is no rearrangement. And in SN1 polar protic solvent will be used, and here polar aprotic solvent will be used. And order of reaction, so you can see the rate of the reaction. Tertiary carbocation is more stable than secondary and then primary, whereas here in SN2 the rate of the reaction for primary will be more and then secondary and then tertiary. And in SN1 the rate of the reaction depends on concentration of only one reagent, which is alkyl halide. In SN2 the rate of the reaction depends on concentration of both alkyl halide as well as on the nucleophile. And here for the SN1 racemization takes place, that is you can see 2 types of product will be formed, whereas in SN2 there is inversion of configuration. So here you can see the rate, step 1 is the slowest step we have seen, therefore it is the rate determining step. The rate of reaction depends only on the concentration of alkyl halide and not on the concentration of the nucleophile. Greater the stability of carbocation, greater will be its ease of formation of alkyl halide. So it depends on stability of carbocation. And then, so here I have written, see the order. So tertiary alkyl halide is, the rate will be more, and then secondary and then primary. And then allylic and benzylic halides show high reactivity towards SN1 reaction, because you know that in allylic carbon, see here if a carbocation is formed here, it is stabilized by resonance. Even here in benzylic halide, so if a carbocation is formed here, it is stabilized by resonance. Therefore they prefer to undergo SN1 reaction. So for the given alkyl group, the reactivity of the halide Rx follows the same order in both mechanism, that is Ri, Rbr, Rcl and Rf. So the meaning is living group. So you know that Ri and Rbr if you take, so I will live faster when compared to that of Br. Therefore, I will be good leaving group when compared to Br. And then comes chlorine and then comes the fluorine. So it is same for both SN1 as well as for SN2. So this will be the order of the leaving group. So I will be the better leaving group. I minus is the better leaving group. So now we will solve this example 6.6. In the following pair of halogen compound, which would undergo SN2 reaction faster? So students, here first remember this. For the SN1, the rate of reaction for tertiary it will be more, and then secondary and then primary. And you have to check the stability of carbocation. For the SN2, primary is greater than secondary, which is greater than tertiary. So this is tertiary. So this will be tertiary. And then you have to check about the steric hindrance. For SN2, you have to check for the steric hindrance. So now we will see the question. So now we will compare in this two, and we will see which would undergo SN2 reaction faster. So here halogen is attached to this carbon, and here halogen is attached to this carbon. So here you know that SN2 mainly depends on steric hindrance. So here this is the primary carbon, and here this is the secondary carbon. So what is the order of the reaction for SN1? For SN1, the order of reaction is, here you can see, primary greater than secondary. So here this is the primary carbon, and here it is the secondary carbon. Therefore this will undergo SN2 faster. And here we will see, so this carbon is primary carbon, this carbon is also primary carbon. So both are primary carbon, and then you see the leaving group. So iodine and then chlorine, which is good leaving group. I minus is good leaving group. So therefore this is better, this undergoes SN2 better than the other one. So here you can see iodine is better leaving group because of its large size. It will be released at faster rate in the presence of incoming nucleophile. Predict the order of reactivity of the following compounds in SN1 and SN2 reaction. The 4 isomeric bromobutanes. So here you can see these are the 4 isomers of bromobutane I have written. So we are going to check SN1 and SN2 reaction. So the rate we are going to check. So here SN1 we can see, for the SN1 reaction what you have to check is stability of carbocation. So stability of carbocation we will see, stability of carbocation tertiary is greater than secondary, which is greater than primary. So here you can see this is tertiary carbon, this is secondary carbon, and here this is primary carbon, and here it is primary carbon. So this will show more SN1 reaction. This comes next. So that is why we are writing order like this. In this two we are going to compare. Both are primary carbon atom. But here you can see, since there is a branch over here, the inductive effect will be more here. Because of more inductive effect, the stability of carbocation also will be more. Therefore, this will show more rate of reaction for SN1 compared to this. So this is 1, this is 2, this is 3, and this is 4. So that is what here the order is given. You can check. Next we will check for SN2. For SN2 what you have to check is steric hindrance. So here you see more steric hindrance is present, and here you can see steric hindrance secondary also there will be more steric hindrance. For SN2 you have to go for primary, which is greater than secondary, and then which is greater than tertiary. So you have to check in this two. In this two again, because of branching, so this will undergo less SN2. Therefore this is number 1, this is number 2, this is number 3, and this will be number 4. And then second reaction. So this is the second reaction they have given. See, I have written the structures for that. So this is first. So first we will check for SN1. So for SN1 what we have to check? Stability of carbocation. So this carbon is primary, this carbon is secondary, this carbon is also secondary, and this carbon is tertiary. So tertiary will be more stable for SN1. So this is more stable, first position. Now in this two we have to compare. So in this two, which is more stable? So here you can see two phenyl rings are present. So resonance will be more here. Therefore stabilization also will be more. Stability of carbocation is more here. So this is number 2 and then this is number 3 and then primary carbon will be number 4. Next we will check for SN2 reaction. For SN2 what you have to check is steric hindrance. So here you can see steric hindrance is more for tertiary. And then secondary, if you compare, here the steric hindrance is more because of two phenyl ring. Here there is only one phenyl ring and one methyl group is present. So here steric hindrance is more compared to this. And here the in primary carbon steric hindrance is less. Therefore for SN2 reaction, this is first place. Primary will be first and then second and this is third and this is fourth. So this is what is explained here. So you can go through it. So next we will see about stereochemical aspects of nucleophilic substitution reaction. Now let us learn about stereochemical aspects of nucleophilic substitution reaction, which is very important. So first let us see what are optically active compounds. When plain polarized light is passed through certain organic compounds, those organic compounds will rotate plain polarized light either in the clockwise direction or anti-clockwise direction. If it is rotated in the clockwise direction, it is called as dextrorotatory and you can represent as small d or plus in the bracket. If plain polarized light is rotated in the anti-clockwise direction, then it is called as levorotatory, and how you will represent is small l or minus in the bracket. So here you can see plane of plain polarized light produced by passing ordinary light through nickel prism is rotated when it is passed through the solution of certain compounds. Such compounds are called as optically active. And then you can see if it is rotated in the clockwise direction, it is called as dextrorotatory. And how do you represent it? D or plus symbol. If it is rotated in the anti-clockwise direction, it is L form and you will represent it as minus. And then molecular symmetry, chirality, enantiomer. So here what you should know is, example, this is the carbon atom. So to the carbon atom, if 4 different atoms are attached, so all these are different atoms, then this carbon is called as asymmetric carbon, or it can also be called as stereocenter, or it is also called as chiral carbon. So remember these 3 words: asymmetric carbon or stereocenter or chiral carbon. So this compound is non-superimposable on its mirror image. Then these compounds are called as optically active. How to identify whether the given compound is optically active is, this is how you can identify. That is, you have to check whether this carbon is attached to 4 different atoms or not. If it is attached to 4 different atoms, then it is optically active. So here you can see if all the substituents attached to the carbon atom are different, then the mirror image of the molecule is not superimposed on the molecule, and such carbon is called as asymmetric carbon, or it is called as stereocenter. So all this I have condensed and I have given here. So just revise this. And you can see this box, chirality. The object that cannot be superimposed on its mirror image is called as chiral. So non-superimposable mirror images. So here you can see these are non-superimposable on its mirror images. So such objects are called as chiral objects. And here these are superimposable. So such objects are called as non-chiral objects. So superimposable meaning is take this and place on this one. So exactly they will fit on each other. That is called as superimposable mirror images. So if it is superimposable, they are called as non-chiral or they are called as achiral. If it is non-superimposable, then it is called as chiral. So let us see two examples what they have given here. The first example is propane 2-ol. So this is propane 2-ol. So check whether it is optically active or not. How you will check? Just now I said that see whether the carbon atom is attached to 4 different groups or not. So this is the carbon atom. See, these two are similar and these are different. So all 4 should be different, only then it is optically active. But here these two groups are similar, therefore this is not asymmetric carbon, therefore this will be optically inactive and they will be superimposable on its mirror image. So here you can see, so this and this you can superimpose on one another, meaning is take this and place on this molecule. So exactly they will fit on each other. So these two are superimposable mirror images, therefore they are optically inactive. Why? Because two similar groups are present. And one more example is given here, butane 2-ol. So again check whether they are optically active or not. This is carbon atom. See, all the groups which are attached to this carbon atom is same or different. CH3, C2H5, H, OH. So all are different groups. Therefore this is optically active and they are not superimposable on its mirror image. So this and this you check whether you can superimpose on one another. So they are not superimposable because CH3 and here you have C2H5. So exactly they are not fitting on each other. So they are non-superimposable mirror image and they are optically active. And some more examples are given, you can see. Examples of chiral molecule. So these examples are given, so you can just make a note of it. So these molecules I have written here. So first one is 2-chlorobutane. So butane means 4 carbon atoms should be there. 1, 2, 3, 4. So 2-chloro means chlorine atom is present at the second carbon. So check whether they are optically active or not. So this is the carbon. So see whether 4 different groups are attached. Chlorine, CH3, H, C2H5. So 4 different groups are present. Therefore it is optically active. Second example what is given? 2,3 dihydroxypropanol. So this is the structure. So check whether it is optically active. This is carbon, hydrogen, then aldehyde, OH, CH2OH. All the 4 groups are different. So this is also optically active. Third example. So here bromochloroiodomethane. So this is the third example. So carbon atom, see here, bromo group, iodo group, chloro group, hydrogen. All are 4 different groups. Therefore, they are also optically active. The fourth example we will see, 2-bromopropanoic acid. So this is 2-bromopropanoic acid. So to the carbon you check hydrogen, methyl group, bromo group, acid group. So 4 different groups are present. So therefore this is also optically active. So they have given some examples. Make a note of it. Next, what are enantiomers? The stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. So here these two are non-superimposable images. Therefore these two will be enantiomers. So remember the definition, what are enantiomers. And then enantiomers possess identical physical properties, namely melting point, boiling point, refractive index. They only differ with respect to rotation of plane polarized light, that is dextrorotatory or levorotatory. So if it is asked, enantiomers, they differ in physical properties, then you have to say no, it is wrong. So they differ only in rotation of plane polarized light. Then coming to racemic mixture. So what is racemic mixture is, if both dextrorotatory compound and levorotatory compound, if it is present in equal amount, then it is called as racemic mixture. The process of conversion of enantiomer into racemic mixture is called as racemization. Identify chiral and achiral molecules in each of the following pair. So we have to identify which is chiral and which is achiral molecule. So chiral molecule meaning is, I already said you that the carbon atom should be attached to 4 different groups. So this is carbon, You can see here hydrogen, OH, bromine and methyl group. So 4 different groups are there. Therefore, this is chiral. And here you can see same groups are present. So this is achiral. And here also 4 different groups are attached. So this is chiral. And here you can see 2 same groups are present. Therefore, this is achiral. And in this is the carbon atom. This is bromo group. This is methyl group. And this side hydrogen. And one more is ethyl group. 4 different groups are present. So this is chiral. And here you can see this is the carbon you are going to check. One side you have this group. One side you have bromine. And here hydrogen and hydrogen. H2 you have to write one up and one in the below. So it becomes hydrogen and hydrogen. Same groups are there. Therefore, this will be achiral. Is that clear? And then retention. So retention we will see when no bond to the stereo center is broken, the product will have same general configuration of groups around the stereo center as that of the reactant. So here you can see this is the molecule what is taken, that is 2-methyl butane 1-ol. So here when it is reacted with HCl, what is happening is this bond is broken. This bond, that is, this is not attached to stereo center. This is stereo center. So stereo center bonds are 1, 2, 3, 4. So these bonds are not broken. Leaving this, the other bond is broken. When the other bond is broken, then the configuration is not going to change. So read once again. When no bond to the stereo center is broken, so stereo center bonds are not broken here, the product will have the same general configuration of groups around the stereo center. Therefore, configuration of this and this will be same. There will be retention of configuration. One more thing what you should remember here is, see here, configuration can be same, but optical rotation can be different. So note this minus sign and plus sign. So this is dextrorotatory and this is levorotatory in nature. Even though configuration is same, optical rotation can be different. And then inversion, retention and racemization. So here this is the compound. So here you can see there is inversion of configuration. So inversion of configuration is, so here you can see hydrogen is on one direction and methyl is on this side, whereas here you can see it is on the different side. So inversion of configuration can take place, or there can be same configuration, retention of configuration. Racemization meaning is if both plus and A and B, that is, this is A and this is B, if they are in equal percentage, 50% of A and 50% of B if it is present, it is called as racemic mixture, because plus and minus symbol can cancel and it will become optically inactive. So see here, if 50 is to 50 mixture of A and B is produced, then the process is called racemization and the product is optically inactive. Why it is inactive? One isomer will rotate the plane polarized light in the direction opposite to the other. Therefore it become optically inactive. So one more important concept, make a note of it, that is SN2 mechanism and SN1 mechanism. We are going to see the stereochemistry. That is, here check what is the type of carbon atom which is taken. So here you can see this is secondary carbon. And here you check what kind of carbon atom is present in this example. So in this example also it is secondary carbon. So here secondary carbon atom is showing SN2 mechanism, whereas here again the secondary carbon is showing SN1 mechanism. So how you will differentiate this? So always remember that if it is tertiary carbon, definitely it will show SN1 mechanism. If it is primary carbon, then it will show SN2 mechanism. If it is secondary, then it can show SN1 or it can show SN2 depending on the type of nucleophile. That is what you have to check. So here both are secondary carbon atoms, but one is showing SN2 mechanism and other is showing SN1 mechanism depending on the type of nucleophile. I'll show you the difference. So in the first one, this is the example. What is the example? 2-bromo-octane. So 2-bromo-octane is allowed to react with sodium hydroxide then you can see octane 2-ol is formed with OH group occupying the position opposite to that of bromide had occupied. So here sodium OH group. OH group is a strong nucleophile. So sodium hydroxide will produce OH minus, which is a strong nucleophile. Always remember, strong nucleophile will show SN2 mechanism. So OH minus will attack this carbon from behind. Therefore, you can see the configuration is going to change. Inversion of configuration will take place in SN2 mechanism. Whereas in SN1 mechanism, it is racemization. Why it is racemization? Because in SN1 mechanism, you know that carbocation will be formed. So carbocation is planar in nature. Therefore, you can see nucleophile can attack from behind or it can attack from front side. So if since some will attack from back and attack from front, so you can see 50% of one compound and 50% of other configuration. Because of that, you can see racemic mixture will be formed. And here you see the example what is taken is 2-bromobutane. Hydrolysis of optically active 2-bromobutane, which results in the formation of butane 2-ol. Hydrolysis meaning is water is used here. So water is a weak nucleophile. So remember, the nucleophile used here is weak nucleophile. If it is weak nucleophile, always remember it will show SN1 mechanism. So that is what, if it is secondary carbon, you should check what is the type of nucleophile which is used. So here it is strong nucleophile which is used, and whereas here hydrolysis meaning is water is used which will produce weak nucleophile. So that is why it is showing SN1 mechanism. If it is SN1 mechanism, then it is racemic mixture. That is 50% of one configuration and 50% of other configuration will be shown. Whereas in SN2, it is inversion of configuration. So configuration will be inverted. So learn these two examples. So students, I hope you are understanding it clearly. So go through it, make a note of all the points. So here you can see all the points I have noted down, and also here at the side I have written, and wherever possible I have highlighted it. So take down all this and revise it. Prepare well for your examination, and if you have any doubts, leave in the comment section, students. I'll meet you in the next video. All the very best. Students, in this video we are going to learn about elimination reaction. So this is the NCERT line by line series. So previous videos, if you have not watched, you can watch those videos. All the important concepts I have written here, and also I have made use of stick notes. So you can see here the stick notes are here, and all the important concepts are written here. You can go through the other videos as well. So here revision will be very easy for you. So within few minutes you will be able to revise the entire concepts. So let us start with elimination reaction. So what is elimination reaction is, from one carbon halogen and from the adjacent carbon if hydrogen is removed, it results in the formation of a double bond, which is called as elimination reaction. So usually here the halogen will be attached to a carbon, and that carbon is called as alpha carbon. The adjacent carbon is called as beta carbon, and in the beta carbon hydrogen atom should be present. So that hydrogen atom and this halogen both will be removed. As a result, a double bond will be formed. So here you can see, when a halogen with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, that is alcoholic KOH you are using. So when you are using alcoholic KOH, elimination of hydrogen from the beta position and halogen from the alpha position will take place, which is called as elimination reaction. It is also called as beta elimination because hydrogen atom is removed from beta carbon. See here, since beta hydrogen atom is involved in elimination, it is often called as beta elimination. If there is a possibility of formation of more than one alkene due to the availability of more than one beta hydrogen atom, so usually one alkene will be formed as the major product. So suppose if more than one product is formed, one will be the major product, and that product will be formed according to Zaitsev rule. So before reading this Zaitsev rule, we will see this example. So 2-bromopentane. So at the second carbon you can see bromine atom is present. So here we said that from the beta carbon, hydrogen you have to remove. So this is the alpha carbon. Halogen will be attached to alpha carbon. So this will be beta carbon, and here this will be beta carbon. There are two beta carbon atoms. So here this hydrogen and this halogen can be removed, and a double bond will be formed between second and third carbon atom. And other possibility is this beta carbon, hydrogen and halogen can be removed. As a result, double bond can be formed between first and second carbon atom. So now two alkenes are formed, pent-2-ene and pent-1-ene. So now one is major, pent-2-ene is major and pent-1-ene is minor. So this is according to Zaitsev rule. So what Zaitsev rule says is, after the formation of the alkene, you should see more number of alkyl groups if it is present, that will be the major product. So here this is the double bonded carbon atom. How many alkyl groups are present? One alkyl group and second alkyl group. So there are two alkyl group attached to the carbon-carbon double bond. And here in this product you see carbon-carbon double bond, and there is only one alkyl group attached. So here there are more number of alkyl groups, therefore this will be the major product. So now we will go through the Zaitsev rule. So what Zaitsev rule says is, in dehydrohalogenation reaction, the preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atom. So here the doubly bonded carbon atom should have greater number of alkyl group. So here there are two and here there is only one. So this will be the major product according to Zaitsev rule. So this reaction is also called as dehydrohalogenation. So dehydro meaning is we are removing hydrogen as well as halogen. Therefore it is called as dehydrohalogenation reaction. So now we have seen about substitution reaction. So haloalkanes can undergo substitution reaction as well as elimination reaction. So when they will undergo elimination and substitution reaction depends upon so many factors. That is, depends upon the type of nucleophile, the type of base, and also the reaction conditions. So here they have given in the textbook, it depends upon, you can see, make a note of this. It depends upon nature of the alkyl halide. So this is the first reason. Second is strength. And third is size of the base or nucleophile. And then reaction conditions. So it depends on all these conditions. So suppose if the nucleophile is bulky, means if it is bigger, so whether substitution reaction will take place or elimination reaction take place. So you can see elimination reaction will take place if the nucleophile is bulky in nature. So you can see this picture. This is the alkyl halide and here this is the nucleophile. So this you can see it is a bulky nucleophile which is present, and this is the carbon atom. And so this bulky nucleophile, it is difficult for it to travel here and attack the carbon. Instead of that, it will remove the hydrogen atom. So this will be acting as a base instead of nucleophile. Therefore, elimination reaction will take place. And if it is a primary alkyl halide, then SN2 reaction will be preferred. So that we have already seen. And if it is secondary alkyl halide, it can be SN2 reaction or it can be elimination reaction. So it can be any one. It depends upon the type of base or the type of the nucleophile. If it is tertiary alkyl halide, it can be SN1 reaction or it can be elimination reaction. So it depends upon the stability of carbocation or the stability of alkene which is formed. So depending on that, you have to choose whether it undergoes elimination reaction or nucleophilic substitution reaction. So you can see in this picture, So here substitution reaction takes place because this is the nucleophile which is smaller. It is not bulky. Therefore, it can go and attack the carbon atom. Therefore, and Br will leave as Br minus. Therefore, here substitution reaction is taking place. Next is reaction with the metals. So here mainly we are going to study about Grignard reagent. So what is Grignard reagent? Alkyl magnesium halide, RMgX. General formula you should remember, RMgX. So the metal which is used here is magnesium. Alkyl magnesium halide is called as Grignard reagent. These reagents are obtained by reaction of haloalkane with magnesium metal in dry ether. So this is very important. We are using dry ether condition, means water content should be absent. So why the water content should not be there? If water content is present, this will be converted back to hydrocarbon. So this can be asked, the reason why it should be under dry condition. If moisture is present, what will happen? If moisture is present, this will be converted into hydrocarbon. Therefore, we are using dry ether. So here first we are taking alkyl bromide. We are treating with magnesium in the presence of dry ether. You can see Grignard reagent is obtained. So mainly here what you should see is carbon metal bond will be formed. Here you can see carbon and magnesium bond will be formed in the Grignard reagent. In the Grignard reagent, the carbon magnesium bond is covalent but highly polar, with carbon pulling electron from electropositive magnesium. The magnesium halogen bond is essentially ionic. So this question can appear in the examination. So see here, this is carbon and this is magnesium. So between carbon and magnesium, the bond which is present is called as covalent bond. So it is covalent bond, still it is polar in nature. It is highly polar in nature. So carbon will pull this electron towards itself. As a result, it will be getting partial negative sign and magnesium will be getting partial positive sign. And the bond which is present between magnesium and halogen is ionic in nature. So because of which you can see halogen will be having partial negative sign and magnesium will be having partial positive sign. So there are two types of bonds present which you have to make a note. So between carbon and magnesium it is covalent bond. Between magnesium and halogen it is ionic bond which is present. So here you can see in the textbook. Grignard reagents are highly reactive in nature and react with any source of proton to give hydrocarbon. So any source which gives proton, that is H plus ion, then it will be converted back into hydrocarbon. So even water, alcohol, amines are sufficiently acidic to convert them to hydrocarbons. So here what they have given is Grignard reagent. Even if a proton source is present, it will be converted into hydrocarbon. So here what the source what is given is water, alcohol and amines. Remember, so in one of the NEET examination it was given water. When Grignard reagent is treated with water, what is the product obtained? So you should know if it is treated with water or it can be alcohol or it can be amine, the product will be hydrocarbon. So it will break here and hydrogen will be attached to R. So you will be getting hydrocarbon. So it is necessary to avoid even traces of moisture from Grignard reagent. So that is why the reaction is carried out in dry ether. So that is why we are carrying out in dry ether. So the reason is even if moisture is present, Grignard reagent will be converted into hydrocarbon. So next is Woods reaction. So Woods reaction is nothing but you are taking alkyl halide and you are treating with sodium in the presence of dry ether. So here you are taking 2 alkyl halide. So take Rx and then Rx. So here Rx and Rx we will take. So the halogen and sodium will be removed and halogen, just a minute, I'll write down the reaction. So Rx, you are treating with sodium and then you are treating again with one more alkyl halide, Rx. So this will be removed and you will be getting R. So this is called as Woods reaction. So next we will see reaction of haloarenes. So this is very important about haloarenes, how they are going to react. So nucleophilic substitution reaction. So usually haloarenes will not show nucleophilic substitution reaction. For that, 4 reasons are given here. So we will see all those 4 reasons. One is resonance effect. So in the resonance effect, what will happen is, you can see the electrons which are present on the chlorine is involved in resonance here with the benzene ring. So it shifts like this, you can see. These are the resonance structures. So here you can see there is a carbon, there is a double bond between carbon and chlorine. Because of resonance, you can see a partial double bond character exists between carbon and chlorine. Therefore, breaking these bonds become very, very difficult. Breaking this bond, that is carbon and chlorine bond, becomes very difficult. Therefore, substitution reaction is difficult here. You can see carbon chlorine bond acquires a partial double bond character due to resonance. Therefore, cleavage meaning is breaking of this bond becomes very difficult. Second is difference in hybridization of carbon atom in CX bond. So here you can see this is haloarene and this is haloalkane. So here this carbon atom is sp2 hybridized. Halogen is attached to sp2 hybridized carbon atom, whereas here in haloalkane, halogen is attached to carbon and this carbon is sp3 hybridized. So here, since it is sp2 hybridized, the carbon is sp2 hybridized, S character is 33%, whereas here the S character is 25%. So more the S character, more will be electronegative in nature. So the carbon atom which is present here will be more electronegative when compared to this carbon atom. So as a result, what you can see is this carbon atom will pull electron close to itself. As a result, you can see the bond length between carbon and chlorine will be less. So that is 169 picometer, whereas in in haloalkane, you can see the carbon chlorine bond length is bigger, which is 177 picometer. So it has a longer bond. So if it is short bond, it is difficult to break this bond. If it is longer, you can easily break this bond. Therefore, in haloarene, again it is difficult to break this bond because the carbon atom is sp2 hybridized, and because of which the bond length will be shorter. So this is the second reason. Third reason is instability of phenyl cation. So phenyl cation meaning is, suppose if this is the benzene ring to which halogen is attached like this. So when you remove this halogen atom on the benzene ring, there is a carbocation, there is a positive sign which is formed. So now this is called as phenyl cation. So phenyl cation is highly unstable in nature. So this is a positive sign on the carbon atom. So this is called as phenyl. This is called as phenyl cation. Phenyl cation is highly unstable in nature because it is not stabilized. So this is one reason why nucleophilic substitution reaction will take place. Particularly, you can see this SN1 mechanism is completely ruled out. Why SN1 mechanism is completely ruled out? Because SN1 mechanism proceeds through carbocation formation. So here carbocation formation results in instability. It is unstable in nature. Therefore, SN1 mechanism is ruled out. And fourth one is very simple, because of possible repulsion. Suppose if a nucleophile approaches here. So here suppose if this is the haloarene. So you know that inside the benzene ring there are double bonds. So benzene ring is electron rich. Nucleophile is also electron rich. So if both are electron rich, you know that they will repel each other instead of attraction. So therefore nucleophilic substitution becomes very difficult. So these are the 4 possible reasons why haloarene will not show nucleophilic substitution reaction. It is very difficult to show nucleophilic substitution reaction because of 4 reasons. One is resonance effect. Because of resonance effect, a partial double bond character will exist between carbon and chlorine. Therefore, it becomes difficult to break this bond. Second is difference in hybridization of carbon atom. So in haloarene, the carbon atom is sp2 hybridized. In haloalkane, it is sp3 hybridized, because of which the carbon halogen bond length becomes shorter. Therefore, it is difficult to break the bond. Third is instability of phenyl cation, and fourth is because benzene ring is electron rich. So nucleophile is also electron rich. So therefore, they will repel each other. So till now what we have seen is it is difficult for the haloarenes to show nucleophilic substitution reaction, but under drastic condition they are going to show nucleophilic substitution reaction. So these are the examples we are going to study for that. That is replacement by hydroxyl group. So here take chlorobenzene. So here you can see the drastic conditions here. Temperature is very high, 623 Kelvin you have to maintain, and pressure you have to maintain 300 atmosphere. So in the presence of a base and H plus ion. So when you are treating with the base NaOH, so this will be replaced by ONA. So here remove this Cl and write here ONA, and then this should be acidified with H plus ion. When it is acidified, this will be converted into OH. So here you will be getting the product. The presence of electron withdrawing group like NO2 group at ortho and para position increases the reactivity of haloarenes. So here you can see NO2. NO2 is a electron withdrawing group. So if it is electron withdrawing, it reduces the electron density now. So when it is reducing the electron density, then the nucleophile can approach this. Therefore, here you can see the temperature here it was 623. So when an electron withdrawing group is present, temperature see here it is reducing to 443 Kelvin, 443 Kelvin. So you can replace chlorine with OH group. And if two NO2 groups are present, electron withdrawing groups are present, so it will reduce the electron density of the benzene ring further. So because of which you can make a note of this temperature. Still at lower temperature you can see chlorine group will be replaced by OH. And here you see when 3 electron withdrawing groups are present, so it reduces the electron density on the benzene ring. So even slightly if you warm it, so you can see here chlorine will be replaced by OH group. So here what you have to learn is a temperature. So at higher temperature, so you can see here the chloro group will be replaced by OH. If one nitro group is present, so temperature you have to make a note, 443 Kelvin, you can replace chlorine with OH group. And then 368 Kelvin, and then if 3 electron withdrawing groups are present, even if you slightly warm, you can convert Cl to OH group. So we have seen that electron withdrawing group should be present only at the ortho and para position. So if it is present at the meta position, it doesn't have any effect. So the reason is given here clearly, you can see. See here, if nitro group is present at the para position, these are the resonance structures. So in the resonance structures, you can see negative sign is present at the ortho position. Here it is present at the para position. Here the negative sign is present at the para position. So when the negative sign is present at the para position, nitro group is also present at the para position. So this negative sign will be in resonance. So negative sign, single bond, double bond. So they will be in resonance. So they will stabilize it. Therefore, at the para position, if it is present, it will reduce the electron density. So this electron density will be pulled by the nitrogen. So it also undergoes resonance. If it is present at the ortho position, see here, nitro group is present at the ortho position. So even then resonance structures you observe, negative sign is present at the ortho position, para position and ortho position. So when negative sign is present at the ortho position, so this will be in resonance with the nitro group, because negative sign, single bond, negative sign, single bond and then double bond. So they will be in resonance. Therefore, electron density they are going to reduce. So therefore, even at the ortho position it is present, it will reduce the electron density. Whereas if it is present at the meta position, so observe this resonance structures. Negative sign is present at the ortho position, at the para position, and at the ortho position. So at the meta position there is no negative sign at all. So therefore nitrogen cannot take that negative sign, or it cannot reduce the electron density of the benzene ring. Therefore nitro group present at the meta position doesn't have any effect. So that is what is given here. Clear explanation is given why nitro group present at the meta position doesn't have any effect. It is because in the resonance you can see negative sign is not present at the meta position. Therefore they cannot reduce the electron density. Whereas in ortho and para position, negative sign is present at the ortho position and para position. Therefore they can reduce the electron density. So go through this. Next is electrophilic substitution reaction. So haloarenes will not undergo nucleophilic substitution reaction, but they are undergoing electrophilic substitution reaction. So here you can see such as halogenation, nitration, sulfonation, and Friedel-Crafts reaction. Halogen atom, beside being slightly deactivating, is ortho-para directing. So here you can see chlorobenzene or halogen is present. So halogen usually it will show minus I effect. So here I have written, you can see here, halogen they are deactivating group because they show minus I effect, but they also show plus M effect. By plus M effect they will show ortho para, they are showing ortho para directing groups. So here you can see due to resonance the electron density increases more at the ortho para positions. So here because of this plus M effect, you can see negative sign is present at the ortho position and as well as the para position. Therefore they will show ortho para directing groups. Further, the halogen atom, because of its minus I effect, has some tendency to withdraw the electron from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene. So now halogens are showing minus I effect. So therefore they will pull this electron, the electron which is present here will be pulled towards the halogen. So they are decreasing the electron on this carbon. So therefore they are deactivating group. Remember that always in halogen, since they are showing two effect, minus I effect they are showing as well as they are showing plus M effect. But what is dominant in halogen is minus M effect is dominating in halogens. So now we will see first halogenation. So in halogenation, remember that here you are treating with chlorine in the presence of anhydrous ferric chloride. So you will be getting ortho product as well as para product, and para product is found to be always major. Here which is the electrophile formed? This is electrophilic substitution reaction. So the electrophile which is formed here is Cl plus. So from here hydrogen which is present here, remove this hydrogen and replace with H plus. So Cl will come and attack here. So therefore you are getting a chloro group here. So the electrophile which is formed here is Cl plus. And in nitration we are going to use concentrated sulfuric acid and nitric acid. So the halogen which will be produced here is NO2 plus. So here you should know the electrophile which is produced. So in nitration the electrophile which is produced here is NO2 plus. So you will be getting ortho product and para product. The major one will be the para product. And then sulfonation. Sulfonation is treating with concentrated sulfuric acid. So here the electrophile which is formed here is SO3H plus. So this is the electrophile which is produced. So at the ortho position one product you will get and para product you will get. The major one will be always para product. So you can remember. Next is Friedel-Crafts reaction. So Friedel-Crafts reaction, you have two types of reagents, that is alkyl halide and acyl halide. Acyl halide is CH3COCl. So this is acyl halide. and here you have to use anhydrous aluminium chloride. So here what is the electrophile which is produced? Here the electrophile produced is CH3 plus methyl cation will be formed. So CH3 plus will be attached to the ortho position or at the para position. Always remember para will be the major product. And here acyl chloride. So here which is the electrophile which is produced? CH3 C double bond O plus. This is the electrophile which is produced. So at the ortho position it will get attached and then para position. So the major will be the para product. So this is Friedel-Crafts acylation and this is Friedel-Crafts alkylation reaction. There are two types of Friedel-Crafts reaction, alkylation and acylation. So if you want to study the mechanism, so you can go through the playlist. I have taught even the mechanism, how it happens. So now we will solve the example sums. Although chlorine is an electron withdrawing group, yet it is ortho-para directing in electrophilic aromatic substitution reaction. Why? So you know that it is deactivating group. It shows minus I effect. So because of which you can see that here it is taking electron towards itself because of minus I effect. So the positive sign which is formed here on the carbon atom, so it is pulling the electron towards itself and it is destabilizing. So inductive effect will destabilize the intermediate carbocation which is formed. So here carbocation is formed. So that carbocation is destabilized by chlorine atom by pulling the electron towards itself by minus I effect. And here because of resonance, you can see here because of resonance it will be showing, it will be stabilizing this plus I effect. These electrons are moving here, so it is stabilizing this carbon atom. So resonance effect stabilizes the intermediate carbocation which is formed. The inductive effect is stronger than resonance and causes net electron withdrawal and thus causes net deactivation. So deactivation will be greater. Why? Because minus I effect is dominant over plus M effect in case of halogens. So this point is very important. Make a note of it. So next we have Wurtz-Fittig reaction. So here in Wurtz-Fittig reaction what you will take is, you will be taking aryl halide and then alkyl halide in the presence of sodium dry ether. So you will be getting this alkyl group will get attached to the aryl group. So this is the product which is formed in the Wurtz-Fittig reaction. So just now we have seen about Wurtz reaction. In Wurtz reaction you will be taking 2 alkyl halide. Here aryl halide and alkyl halide. In Fittig reaction you will be taking 2 aryl halide. So 2 aryl halide when you are treating with sodium in dry ether. So here, so this is 1 aryl halide. You are treating with sodium and then this is another aryl halide. So here this will be eliminated, 2 NaX will be eliminated and you will be getting the product like this. So this is the product which is obtained. Now we will solve in text question. Which alkyl halide from the following pairs would you expect to react more rapidly by SN2 mechanism? So we will see which one will undergo the rate of SN2 mechanism will be shown higher. So this is first one and this is second one. So you know that in SN2 mechanism, primary, the rate of primary alkyl halide will be greater than secondary and then tertiary. So now we will see here halogen is attached to this carbon which is primary carbon and here halogen is attached to secondary carbon. So primary carbon the rate will be more. So you have to write this is the one which shows the rate will be higher. And in this two we will see, so halogen is attached to secondary carbon and here halogen is attached to tertiary carbon. So secondary carbon the rate will be greater. So the answer is this one. And here halogen is attached to primary. Here also halogen is attached to primary. So this is very important. So when it is attached to primary carbon, so next what we have to check is about steric hindrance. So if here you can see there is a branch. So if the branch is closer to halogen, so here you can see branch is closer to the halogen. So steric hindrance will be more. If steric hindrance will be more, the rate will be less. So here the rate is less. Therefore, the rate will be more in this case. Next, in the following pairs of halogen compound, which compound undergoes faster SN1 reaction? So for SN1 reaction, the rate of reaction will be greater for tertiary and then secondary and then primary. So here we will compare this two. So here halogen is attached to tertiary and here halogen is attached to secondary. So the rate will be greater in tertiary. And here we will compare this to halogen is attached to secondary, halogen is attached to primary. So therefore the rate will be greater in secondary. So now identify A, B, C, D, E, R and R dash in the following reaction. So we'll do this now. So we are treating this reactant with magnesium in dry ether. So what is the product you are getting? So magnesium means, remember, this is a Grignard reagent, magnesium with a dry ether. So Grignard reagent, so what the product you will get is, you will be getting, so here carbon magnesium bond will be formed, MgBr. So this is the product obtained. So always remember, between carbon, so this is carbon and this is halogen. When you are treating with magnesium, between carbon and magnesium bond will be formed. So here you can see carbon magnesium bond is formed. When you are treating with water, so I told you that it can be water or it can be alcohol or it can be amine. So they will donate proton, because of which here you can see hydrocarbon will be obtained. So this is going to break and here H will attach. So the product will be, so B will be this. So B is this. Next. So RBr, again you are treating with magnesium in dry ether. So again it is a Grignard reagent, you will be getting C. And here this C, when you are treating with D2O. So instead of water, here deuterium oxide is given, D2O. So you are getting this product. So here D is attached to this carbon. So meaning is, see here we are removing this MgBr and we are attaching hydrogen here. So if D is attached to this carbon, meaning is here MgBr was present. So here you can write. So C will be this, CH3, CH, CH3, and here it will be MgBr, MgBr. So here what is R then? So R will be, so if you remove this MgBr, so see here RBr, you are treating with magnesium. So you know that magnesium will form bond between carbon and magnesium. So this you have to remove. So R will be, so this will be CH3, CH, CH3Br. So now once again you go through this. CH3, CH, CH3Br. When you are treating with magnesium in dry ether, what happens is, between carbon and magnesium a bond will be formed here. Therefore you will be getting CHMgBr. When you are treating with the D2O, so this will be removed, in that place deuterium will be attached. So C will be this. So next we will see R-X when you are treating with sodium in dry ether. So sodium in dry ether, meaning it is Woods reaction. So always remember, sodium in dry ether will be Woods reaction. So here this is the product formed. So meaning is, this break this into two. So this is one alkyl group and this is second alkyl group. So here R dash would have been this, CH3, CH3, CH3 and X. So here two molecules will combine together. So same two molecules will combine together and this Woods product you will get. And this side, this when you are treating with magnesium, so this is Grignard reagent. When you are treating with magnesium, what will happen? Between this carbon and magnesium a bond will be formed. So it will be CH3, 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 MgX. And when you're treating with water, so this one you're treating with water. So when you're treating with water, so here this will give CH3, CH3, CH3 and H. So you're removing this MgX and you're placing hydrogen. So this is E and this is D and this is R dash X. So this completes haloalkanes and haloarenes. So students, go through it. It's very important. So go through NCERT at least 5 to 6 times. You will have to revise. Only then you will get confidence in NEET examination to solve any kinds of questions. So here you can see in this chapter all the important points I have written at the corner, and also stick notes I have written. So revise this several times so that the concepts becomes clear to you and you can attempt all the questions. So all the very best students. I'll meet you in the next video.